All right, hello from the other side, and let's start right away setting our work directory, Abaqus tutorial 1, fast punch. We'll define, let's save the CAE fast punch tutorial. All right, parts, 2D discrete rigid wire. Approximate size, we can also go smaller here because we know it will be quite small. I don't know why it takes so much time. So we'll use the create spline through points. And I think I provided you, what's going on? Yeah, this server actually cost, I don't know, 2,000 euros. And it's not been able to, yeah, it's impressive. Let's wait and see what happens. I don't know. Maybe this is the time to switch to, I don't know, Twitch. I don't use that kind of stuff. YouTube, good documentary. I can really recommend How the Universe Works. Nice things. Or Modern Marvels. That's a nice engineering documentary series. Okay, so I don't know what happened. Let's go. If we're lucky, maybe we can reopen the CAE if we redefine fast punch, yeah, open. Yeah, looks good. Do not recover changes, no. We'll start over. To the discrete rigid wire size. Okay, let's go down to 1. Spline. I'll provide you the points, so it's minus 0.2 and 0.2 upper left. Okay, we can see it. Then it's minus 0.10, so 1 at the bottom. Then we are at 0 and 0.2, the one in the center. Then we go to 0.10, and then we go to 0.2, 0.2. All right, that looks about right. All right, don't be confused by this coarseness. This is just the visualization. We talked about this, right? Tools, reference point. We'll pick the top left. Parts, part 1. Engineering features, inertias, point mass. Continue, we assign it to the reference point. Just give whatever value here, it doesn't matter because you'll prescribe everything here. It just needs for the calculation. And as I pointed out, I think from 2017 on, Abaqus actually does this for you. Okay, let's maybe finish the meshing right away. We'll set global seeds at a size of 0.01, deviation factor of 0.05. And here we go down to 0.001. Okay, let's see. Yeah, it looks good. See, you've seen it's a little denser in the region of interest, so where you have the high curvature. And yeah, R2D2 element, we don't have a lot of options here. We can continue with the block. It will be a 2D deformable shell, approximate size 1. What did I say? We go from minus 0.20 to 0.2, 0.2. I hope that is right. Okay, yeah. Looks okay to me. And now we'll petition, use the petition phase option, and then we'll just sketch a vertical line just dead center. And yep, now we have the two distinct things that we could also mesh separately. That's also a cool thing. The global seeds we'll define as 0.01. Yep. And the mesh then looks like this. What we can now further do is that we give a vertical bias at the edges. Single bias going from 0.006 to 0.03. Yeah. But we have to, of course, as always, I don't know. It's like if you plug in your USB stick, it's always the other way around. For some reason, you always have to flip the bias. I don't know. It feels like a curse. So why are we doing this? Because now we know these elements won't necessarily contribute much to the simulation, so we can save some computational time here and rather invest it on top. However, yes, you pointed out correctly, 100 rubber points for you. Now we actually decreased the vertical element length. So here I'm kind of undecided whether I actually want to do it or not. So maybe I actually go back. Maybe I delete the, I believe we don't gain anything if we do in an explicit, in static implicit analysis. I'm with you guys. I would do this biasing, but here actually I would keep it the way it is, because your LE is larger here, so your overall simulation will be done faster if we use this kind of mesh. And CPS4R, yeah, looks good. In this case, the default option actually likes me. So we'll continue with the material. We said man of steel. Now here it is, density. You cannot run your explicit dynamic simulation without specifying the density, because otherwise your algorithm wouldn't know the dilatational wave speed. So we go 785 E3. We define the elastic parameters as 210 E9. I didn't give the Poisson's ratio. Let's go 0.3. Mechanical plasticity, insert row after. So we start at 200 E6 0, and at the very end we have a saturation stress of 600 megapascal. Maybe at 10 if we encounter severe deformations. Maybe we can use 10 here. So sections: solid homogeneous, yeah. Steel, yep. Oh, okay, and now we go sections assignment, whoop. Both sides, after partitioning, you could technically assign different sections to it. I think I said this before. You could go aluminum left and steel right, if you like. So, what else do we got? Assign the section, check assembly, instances. Apply, get the punch, move it up. I don't know, by 1. Whoa. Way up there. Okay. And then use the translation to tool. So movable instance, edge of the fixed instance, start point for direction of contact. So we are going down, and now we go to a distance of 0.05. No, 0.005. So very small, I hope. Preview, see, yeah, imagine here having the full rendering, so there would be a small gap here. So that looks good. They're not in contact right away. This is exactly what we want to do. And now it's time to go dynamic. Dynamic explicit, temperature displacement. We'll probably talk about this in STIMF2 when we deal with temperature and thermomechanically coupled things. But for now, dynamic explicit is what we want to do. Of course, Energium on. There's no way I want one of you guys see a dynamic explicit analysis run with Energium off. But anyways, see, it's automatically set to on. So we have a very small time frame. It's a fast process. And here you see the tab mass scaling. Here we could now, if we create it, scale by a factor of 16. We talked about this at the beginning of the step for the whole model, semi-automatic mass scaling. I won't do it right now, but this is where you would do the variation for if you would like to compare the results of the two. Okay, wait, so we have to switch back to throughout step value here, and now we're good to go. Now what we could do, if we're in a step module, we could, using the other tab, we could create a domain, an ELLI domain, and use adaptive ELLI mesh below. And then here we define the region, and let's pick the left partition of it. And you can go into all the details. So ELLI has tons of options, controls that you can specify. Start with the default. You will have a huge benefit from using ELLI under certain conditions just by using the default. If you want to further improve it, really dive into it, check out all the options you have. And the two things that you can alter right away are the frequency. So how many times do you do this? So you run for 10 increments, stop, do an ALE step, run another 10 increments, stop, do another, and so on. And these sweeps are the number of ALE runs each time you stop. So the amount of displacement you move your nodes within one ALE sweep is not actually very large. So the maximum you can get by using ALE could be not reached within a single sweep. So sometimes people go to 2 or 3 here in order to ensure that they are at a good result of your ALE whenever you start actually doing ALE. So when you stop the actual FEM simulation. So maybe let's go to 10.2 here. Okay, so we assigned ALE interactions, surface-to-surface contact, master surface, of course, the stiffer one. The yellow side will get into contact. Second type is this and this. See, you could even specify different types of contacts between left and right here. So partitioning really is a cool way to have something like compare the results right away. But remember, the material, it is one body here, so it's affecting itself. Okay, so you see that contact looks much easier in explicit dynamic analysis because, yeah, basically everything is taken care of. All you need to still do is in the same fashion as with the implicit static case, define the tangential and normal behavior. We stick with frictionless and hard contact. Use the defaults here. Okay, we see contact is being activated. Then we go to boundary conditions. We said, yep, we want to encastre at least the bottom. You could further go and select. So if you later on check here and then the region, you could add the edges to it. Here right now, you could add these two edges to do the, I think one of the, I think I didn't put it as an explicit variation, but we talked about this, right? So, and the second boundary condition would be the vertical for this one, and it is -2. And yep, you remember correctly, use the amplitude here. So we don't want to have like this instant jump in velocity, but we want to use a smooth step amplitude for our velocity. And what you quite usually do is over a period of 1/10 or 100th. So you start at the frequency of 0 at the time 0, and then after, let's say, 100th of a second, you are at your 100% amplitude. So this is like a percentage. So 1 is 100% of your amplitude. So you always have to multiply this value times the value you actually assign to your velocity boundary conditions. So if I would go 0.5 here, after 100th of a second, it would run at 1 meter per second because my unit system is kg/ms/n. Yeah. So this is 2 meters per second. And if you imagine this was very small here, now you understand why we only need a simulation time of 500ths of a second. So I hope we actually defined everything that we need. So we could create a job and yep, just give it a try. And now I would like to show you guys using the monitor. Okay, we have a warning. We should check that out. Yeah, displacement, see, it actually, for warnings on any jumps prescribed is cross the step. Yeah, this is exactly what I talked about. Use velocities, though in Caster, yeah, in Caster is just right from the beginning, no movement. So in this case, you can ignore this. And here you see your delta t, your stable time increment, and you can see it's very small. Now the simulation is completed, and you can see it is decreasing. And I hope when we now look at the results, let's close this for a second, look at the results. Okay, holy shit, now that's good, that's actually good, what we see here. Remember, left is ALE, right is non-ALE, right? And now we have the good depiction. See, this is the mesh, so we actually see the meshing now. Why is it decreasing? And I think by now you understand it's due to that the critical minimum element across my entire body, so it might be even this case, it's interesting, decreases over time. So your CD stays constant, your dilatational wave speed, but your LE decreases over time. Okay, why did I choose this example? Because with the given setup, we really almost force a numerical instability. Because if this node tries to get into contact with this point at some point has to decide, am I going left or right? And this almost always causes a very distinct behavior, which you see here. So due to whatever numerical instability it chooses to go left, this will actually cause this element edge to be moved right up and left up. That you see here, right? So this element now, the contact, remember the contact is defined by the points and not by the element edge. So the contact is still technically correctly fulfilled. Yeah, that's weird to understand, but this is why the simulation, okay, in explicit dynamic analysis, it doesn't do not converge, it will always keep running, but you will see a similar effect in implicit, though it might have trouble to converge before getting to the end of the simulation. But this behavior, I actually intended to see this behavior. And this causes, even though I said contact is handled very well in Abaqus Dynamic, you can see the beneficial effect of ALE, because even though at some point you see some buckling, in the sense that I think from here on, that your center node, or that your two center nodes do not remain exactly on top of each other. It's not a big problem, because you see the ALE is doing well at maintaining this either parallel or orthogonal. So edges either are parallel to the contact or orthogonal to the contact. And the structure of these columns are very typical for ALEs. And so you see, actually, even though explicit dynamic analysis is good in dealing with contacts, in certain cases, only with using ALE, you can maintain really good contact. And I hope you guys agree that this is a very nice contact here. So it was like a super fast simulation, and yeah, I hope you get an idea of how to set up an explicit dynamic analysis. And you can definitely say this is quite a dynamic process, because It's running at 2 meters per second. It's a very small body, so it's penetrating within a couple of hundredths of a second, and we are dealing with actual mass here. So maybe you see even some dynamic effects like this material being pushed out further up than it would be in the case of a static problem. But I think at these speeds you won't see this kind of behavior. Anyways, for example, what you can also see here, that ELLI, because it uses the same elements, the same nodes, if it concentrates the element density in the region around contact and the regions around high curvature, it has to get the element volume somewhere. And this is why you see the element volume increasing here. And yeah, and if you maintain such a mass, so this critical element length, which probably will be this one here, is at some point definitely larger than whatever the crap you find over here. So if you go to full ELLI, the simulation will be most likely to run faster. And you can actually always check if you go to the result monitor and then go to the status file, it should, the critical element, there you go. So critical element, the number, so it's a 6 to 1. If we now go to and get the element 6 to 1, you see exactly as I expected. This is the element that has the minimum LE. So this weird element, this is exactly what I intended to show you guys. This is exactly the element that defines the delta T. So maybe we can now do one more thing. So let's take one more. So this is at 1.5.7 down here. Let's go to steps and just simply let's pick both as ELLI, and today I'm a bit lazy, not naming everything as I should do it. Sorry guys. So now let's monitor our second job. And hopefully what we will see that our stable time increment at the very end, okay, 1.5 E minus 7 was, yep, you see. So just by using ELLI compared to no ELLI, because like previously the non-ELLI part was the defining part, it's more than, yeah, we cut the computation costs more than half, like 65% or so. Because now, let's check again the critical element. Okay, it's still 600. So sometimes it's, okay, 219 at the end. Let's go to results here. But yeah, it will be still somewhere around here. So was it 219? Oh yeah, over here. So one of these elements then shows the critical element, and was it 619? No, was it? Can't remember. 621. 621. Yeah, it's the one over here, the one that was previously fully distorted. So because ELLI maintained a better mesh aspect ratio and thus maintained a better or a larger min LE, our delta T was larger and our simulation required fewer number of increments in total. yeah, so you see, for example, increments here, roughly 100,000 over here, and 180,000 over here. So that's also another way to look at what you saved. So we saved a lot. So that's good. So keep that in mind. So only a few people do it because they're afraid of the effect on the stress distributions and stuff. But I wouldn't be so afraid. So ELLI is a nice thing in combination with explicit dynamic analysis. And sadly, it can only be used in this case, because if you move the nodes, you wouldn't ensure a static equilibrium. So this is why they don't use this method in static implicit analysis. Okay, guys, that's it from my side for today. I think we talked a lot. I'm sorry, and you can really hear I'm losing my voice by now. But since this was like special topics not covered in lectures, I hope you guys got a feeling for it. And what I can tell you is that more and more people start to using explicit dynamic analysis in metal forming, because contact can be handled very easily, especially when using ELLI. But I just wanted to show you this last option to give you this, especially if you have buckling, it's nice. So if you crush things, if you want to see some folds occurring and different stuff where this comes naturally using explicit dynamic analysis, it's kind of a nice tool, definitely. And especially considering severe mass distortion. There are other options out there, SPH, for example, smooth particle hydrodynamics, which are today misused for large severe deformation analysis. But if you encounter problems using static implicit analysis, maybe checking out explicit dynamic and especially explicit dynamic analysis together with ELLI is a nice option. So do the variations, check it out, learn, watch videos, and yeah, have a good time, guys. Bye.